Hi! In this video, we'll talk about the gradient vector. So here are some of the goals that I have set aside for us for after we watch this video and read this section in the textbook. And we'll start with the definition. Remember that the gradient vector we find by basically sticking together the partial derivatives. So we build a new vector whose x component is the partial with respect to x of our function f, and the y component is the partial with respect to y. And the gradient itself is sort of a function in that we could plug in any xy points to find the vector at that spot. And the symbol we use is a Greek word called nabla. It's not in the Greek alphabet, but that's what we call it. So we would just read this as the gradient of f at xy. So let's remember the first application of the gradient that we saw, and that's in finding the directional derivative. So for this function f, which is 6 minus x squared minus 3y squared, we might want to find the directional derivative at the point 1, 2. So remember, the point 1, 2 is in the domain, and if we're looking at the directional derivative in the direction of 1 minus 1, basically imagine walking that way in the domain and asking what's happening to the function. So in this picture, you can see sort of a shadow. This blue dot on the bottom corresponds to the point 1, 2, and the vector is pointing in the direction of 1 minus 1. And to ask about the directional derivative is to ask, well, what's the rate of change in the surface of the function? How is z changing as we change the position in the direction of that vector? So to find the directional derivative, we can take the gradient at the point 1, 2 and dot it with u, a unit vector in the direction of v. So we've got some work to do. First, we'll find the gradient at the point 1, 2. Well, remember we build the gradient by taking the partial with respect to x and the partial with respect to y to get a vector with two components. In this case, that's minus 2x minus 6y. And then we can plug in the x and y values of the point in question, that is 1, 2. So we let x equal 1, we let y equal 2, and we get the vector minus 2, minus 12. Also, for the formula for directional derivative, we need a unit vector. 1 minus 1 is not a unit vector. It's got a length of root 2. So we can scale it. Hopefully, this is second nature for us by now. We'll scale it to get this vector we'll call u. And then to take the directional derivative, we simply dot these two vectors, minus 2, minus 12, dotted with 1 over root 2, minus 1 over root 2. And the answer is 10 over root 2, or about 7. So if we were to walk along this surface in the direction of the vector v, we would experience a rate of change of about 7 units vertically for every unit we walked laterally. So let's take a look at the contour plot of that function we just saw. The point 1, 2 in the domain is here, and I'll draw the gradient vector. Well, at least I'll draw the direction of the gradient vector. Remember, the gradient is minus 2, minus 12, which is too big to fit into this picture, but this arrow I'm drawing gives you the idea. So I'd like to know from this point 1, 2, in which direction would we see the greatest increase? That is the largest value of du f12, the most negative, or maybe where the direction is 0. I'm sorry, the directional derivative is 0. And our answers here are a preview for what's coming next. So we can ignore the gradient vector for the moment and just think about what we know about contour plots. Starting at this point 1, 2, if we wanted to see the fastest increase in the value of f, we should walk as directly as we could towards the next largest contour. So we're somewhere between the -10 and the -5 contour. We should make a beeline for the -5 contour, maybe walking in this direction. The same, sort of the opposite is true. If we wanted to see the steepest decrease, we should walk towards a lower contour. And if we wanted to see no change at all, we know the answer is to walk along a contour line. Well, this 0.12 is not on a contour line, but we can imagine if we had more contours that the contour line should be essentially parallel to the ones around it. So these two purple arrows I'm drawing would be directions we might see no change at all. And you can think about how those all compare to the gradient vector that I drew. In the next video, we'll write down carefully these observations and how they relate to the gradient vector.